Thanks for the transition. Good morning. Yes, I'm Julien Milli. I'm an astronomer at IPAG in France. And for the next 30 minutes, I'll be talking about the lessons learned in ground-based instruments. And first, I'd like to thank the organizer for inviting me. It's really an honor to be there. I was back as an attendee 10 years ago at the 2014 Sagan Summer School. I have extremely good memories of that summer school, and I'm happy now to be on the other side as a panelist. So thanks for the invitation. And since that time, I've been working quite a lot at the VLT, the Very Large Telescope at the European Southern Observatory, 7 years before coming back to France. And this is why most of the illustrations that I'll be presenting in this talk are based on my experience at the VLT, mostly with the sphere instruments, so the high contrast imager sphere. But I know that also some of you may be also exposed to other of the high contrast imagers like GPI, for instance, MAGEO. So I'll be trying to make also references to those instruments. And last point, yeah, for personal reasons, I've stopped flying, so that's why I'm not present among you today, but I hope you'll be able to bear with me remotely for the next 30 minutes. So here's what I'll be describing for in my talk. What is currently limiting the contrast? What is limiting us? What have we learned? And some perspective. So let's jump right in the topic. I'd like to give first a historical perspective. Most of you probably haven't seen some of the first generation high contrast imagers. For instance, here is an example of NACO at the VLT, which was installed before Sphere. And you see here a sequence of the point spread function in the H-band of NACO. So you see it's moving around, it's very dynamical, it's asymmetric. You have speckles with various time scales. Most of them are from the turbulence, so they are moving quite fast. Each frame is about a second. Some of them have a longer time scale, they are quasi-static. And the reason for that is that the adaptive optics correction was really driving the design of the instrument at the time, and not so much the stability. We're not so much interested in contrast, much more on having already a good adaptive optics correction and correction of the turbulence. For instance, the pupil stabilization, which is really key to reach a high contrast, was not installed at the start. It came on later on on NACO, and there were various flexures of the instrument giving rise to a lot of instability on the PSF. Coronagraphy was also just starting at the time, and this image here is saturated in the center. The black dot that you see at the center is actually not a coronagraph, it's just the saturated pixels. So the contrast was limited. And now with second generation high contrast imager like Sphere, GPI, MAGEO, we have much more stable point spread function or coronographic images. Here you see a sequence varying on the timescale of minutes, as you see. Those systems were based on first generation system, but really with a high density of actuators, high number of subpupils for the wavefront sensing. The focus was really put on stability, diffraction control on coronography to really keep track of and monitor very well and minimize the speckles. Dedicated low order wavefront sensors with low non-common path aberration calibration strategies. Also different strategy to allow to do differential imaging as a post-processing technique, and post-processing was really thought of from the design point of view of the instruments. And then the contrast was really the new matrix rather than the Strel ratio. I think you've heard of all these terms already in the previous session, especially on Tuesday with Faustine and Becky, who gave talks about those topics. So what was the performance of those instruments, and have we really fulfilled this promise to get high contrast and have a 90% Strel all the time? So first of all, let's just recall the Strel ratio tells us how close we are from the diffraction limits. So 100% is we're diffraction limited, and with 0% we are seeing limited. So what you see in this plot is a summary of the performance of the sphere instruments with the Strel plotted vertically as a function of the magnitude, the visible magnitude of your target. And you actually see that we're not always at 90% Strel as we were maybe expecting at the beginning. We are there for bright targets in good conditions, but as soon as the target gets fainter, so maybe fainter than a visual magnitude of 7 or 8, then you see the strail is dropping. And it's also the case when the conditions are bad. So here you have two colors for the line for long coherence time, greater than 5 milliseconds, or shorter coherence time, smaller than 5 milliseconds. And you see when the evolution, the turbulence is evolving very fast, so low coherence time, the strail is dropping. So there is still some work to do, and you see that coherence time is critical. And that was actually one of the, so here is the same plot where here the color shows you the coherence time. You see that we're on the top of the envelope with long coherence time. And so the fact that the conditions actually still do matter, even for extreme adaptive optics system and high contrast imager, it was one of the first lessons we learned from those instruments. And actually at the VLT, at the Very Large Telescope, when SPHERE came online, we introduced coherence time and seeing as the two parameters that an astronomer can request for his observation to be done in good conditions. Before that, only the seeing was a parameter that an astronomer could say, okay, I want an observation done under seeing smaller than such and such. So we made this, and so in this plot you can see here how the coherence time evolves with seeing. You have this kind of comma shape diagram, and the various lines show you the different turbulence condition that you can request at the VLT. For instance, you can request the top 30% atmospheric condition, top 50%, or top 70% if your observations are not too challenging. So that also drives the need for accurate turbulence predictions, and this is also an area which is really developing now with some seeing and coherence time prediction for various observatories. And you can see in this set of images that actually, indeed, the conditions really do matter. These are signal-to-noise maps of the system 51 Eridani. So one of the first exoplanet to be imaged by the GPI instruments. And these are images done at several epochs, four epochs, under various conditions. The strail was almost always in the 80 to 90% range, so always good. But as you can see, in some cases we have a high signal to noise, like in the second image, and in the third image you see that it's actually the planet is actually not there. So 51 Eridani is really a challenging planet. It's a low mass, it's relatively low mass, and really here you see that the conditions matter quite a lot, and especially the coherence time. So I told you now with new high contrast imagers, the contrast really became the new matrix. So what's happening if we look at the contrast? Here you see the contrast as a function of the H-band magnitude for various targets that were part of the SHINE survey, so the VLT SPHERE survey that Clémence introduced you in the last presentation. And as you can see, and the color code is for the strail ratio. And as you can see, even when we only look at observation done under high strail ratio, so from 80 to 100% strail, you can still see some variability in the contrast between 10 to the minus a few times 10 to the minus 5 to a few times 10 to the minus 3. And the reason for that is that the strail is really an integrated quantity. It tells you how much wavefront error you have, but it doesn't tell you where this wavefront error happens, at which spatial frequency. And to know that, you really need to look at the power spectrum distribution of the wavefront error if you want to understand where your error comes from. So we typically call this wavefront error, we call it sigma phi, shown here in this equation, and we can decompose it in various terms coming from the various contributors to your budget error in an adaptive optics system: the fitting error, the aliasing, servo lag noise, calibration, or non-common path aberration. And we'll see in the next slide where all those errors actually play on your contrast curve. You see here a contrast curve. So in dashed line, this is the raw contrast. In plain line, this is the final contrast after star subtraction. Here, this is done with the PACO algorithm that Faustine introduced on Tuesday. The various colors are for various atmospheric conditions, so top 30, top 50, top 85%. And actually, what the shape of this curve really tells you where what type of error dominates. And I will explain you that here, where we've split the various error terms. So the top curve that you see, if you see my mouse here, the total blue curve is your contrast curve. And we've decomposed various terms. So you see the fitting error. The fitting error is the black curve that only plays a role on the outer parts. You have an adaptive optics correction radius, which correspond to the number of actuators divided by 2 times lambda over d. So typically for a system with 40 actuators on the diagonal, for instance, that would be about 40, that would be 20 lambda over d, so about 800 mass milliarc second for in the H-band for an 8-meter telescope. And if you only consider the fitting error, this is how your coronographic image would look like in the assumption of a perfect coronagraph. So only residual outside your adaptive optics correction radius, because you have perfectly corrected all the spatial frequencies within your the degree of freedoms that are available with your deformable mirror. But that's not the only contributor to your error. You have also aliasing. Some spatial frequency, I'll come back to that, are high spatial frequency, but are seen as low spatial frequency because of your wavefront sensor. So that would put back some energy inside your AO correction radius, and this is the red curve here. Then you have servo lag error. I'll come back to that in a moment also. This is when you have a wind or if the turbulence evolves faster that your system can correct for. And that is what is limiting you in the innermost parts of your, close to the inner working angle of your chronograph. Exactly like low orders that are not presented in this diagram, but that also limits your contrast at small separation. So let's go now through all these terms to see how they really affect our contrast. So first of all, I told you about this fitting error with the extreme adaptive optics systems. This is really the first time that we could clearly see the adaptive optics correction radius, which is seen in this series of images here in the J, H, okay, then you see it scales with wavelength because it's proportional to lambda over D. And that corresponds to really the highest spatial frequency that you can create with your deformable mirror. So it corresponds to the number of actuators over 2 times the number of cycles per pupil. Then I told you there is also this aliasing error. And aliasing is something that I guess you are familiar with. It's when you have a signal, like in in 1D, that would be the red signal that you see here. And you sample it with a sampling frequency which is not high enough. And then in this case, when you sample it with the black dots, for instance, you have the impression that you are sampling a signal at a low spatial frequency. And then if you correct for this low spatial frequency, while it is a high spatial frequency, you will introduce some error, which is called the aliasing error. And to cope with that, we've introduced in high contrast imager a spatial filter that is basically just a diaphragm in a focal plane to cut all the high spatial frequency that you cannot correct for. But of course, if you close your spatial filter, you also have less light. So in bad conditions, we cannot close it as much as we would like to. So it's always a trade-off. And this trade-off is really visible, as you can see in this series of images where we progressively close the spatial filter from 2 lambda over D to 1 lambda over D. And you see that you really clean the correction radius in your image. So these are real images obtained with sphere on sky. Then a big contribution to your budget of error is this servo lag that we also call the temporal error, or also the wind-driven halo. There are several terms. Why do we call it the wind-driven halo? I think you will understand very easily through this video. This video shows you the series of images, coronographic images obtained with sphere over about an hour. And the black arrow shows you what is the direction of the wind in altitude at about 12 kilometers in what we call the jet stream layer. I can show you another, which is even more dramatic. You clearly see here that there is a huge halo because the adaptive optics just cannot correct fast enough in the direction when the wind blows. So the wavefront is evolving faster than we can correct for. The red curve here is showing the ground wind speed, but we will see, I think in the next slide, that it's not really, the wind-driven halo is not correlated with the wind at the ground in most cases, actually. This is what I want to show you here. So if we just measure the direction of this wind-driven halo, so the direction where it's elongated, we plot it vertically, and horizontally we put the wind direction at various altitudes. So meteorologists like to speak about in pressure rather than in altitude, but the different plots that you see here really corresponds to altitudes. And in most cases, the curve is relatively flat, but you see that for some pressure levels, like for instance, 200 hectopascals, there is a slope indicating that the wind direction, the direction of your halo is really correlated with the direction of the wind speed. And 2 hectopascal corresponds to about 12 kilometers. That's shown here on this graph. You have the slope of this fit as a function of the altitude, this time in kilometer. And you see that's about 12 kilometers when we have the jet stream. It's very well correlated. So we're really we're sensitive to the jet stream that makes the wavefront evolve very fast. And the reason is because in the jet stream, we have relatively high speed, high wind speed at about 40 to 50 meters per second. But it's not the end of the story. You probably have noticed that this halo is also asymmetric. One lobe of this butterfly pattern is brighter and more elongated than the other one. So this is something that Faustine Cantaloupe studied, and we showed that it's actually due to the fact that it happens at a certain altitude. So it's not in a pupil plane, and we have some Fresnel propagation effects that make it asymmetric. And it's really the combination of this very high wind speed and the propagation through these 12 kilometers of altitude that makes this pattern asymmetric. There are various ways to correct for that. Of course, the best way is just to go faster, to have a very high loop frequency. That's the case, for instance, on Subaru, going as fast as 3.6 kilohertz. It's going to be the case also for future grade of sphere, Saxo Plus, for instance. You can also use predictive control algorithm to cope for that, or you can you can choose your observing slot. You can observe when you have slow wind speed, for instance. And for that, all the months in the year are not equal. The very high wind speeds, so 40 meters per second, for instance, in jet stream typically happen in the winter in the southern hemisphere, and the summertime is really the best. The direction is also not equal. Most of these wind speeds are typically west to east wind speeds, so you mostly see this pattern in a specific direction. Okay, so that's all for the servo lag. Let's now go to the noise in your wavefront sensor. So I've already shown you that for fainter star, we have we decrease the contrast, we decrease the shrill, and so it's becoming the dominant error term for faint stars. And so this is why we favor very sensitive cameras for wavefront sensing, for instance, EMCCD. So this is the case for most high contrast imager. It was not the case for GPI, but it's going to be one of the upgrade that takes place in GPI 2.0. And you also have heard from Becky's lecture on Tuesday that the noise propagation is not the same for all wavefront sensor. And this is why we really now favor the pyramid wavefront sensor that are more sensitive to low order aberrations. And so Skexeo, Mageo, KPIC, they have all these kind of pyramid wavefront sensor. That's going to be also the baseline for Sphere Plus, for instance, the upgrade of Sphere. And as you can see on the graph on the left here, that most of the stars, most of the young association where we would be interested in looking for exoplanets or disks, they are actually most of them around from 12 to 16 magnitude in the R band. So we really need to push to go to fainter stars and redder stars if we want to reach those targets. Then I'd like to give a word on calibration errors. And one specific calibration problem is the low wind effect, which was really a discovery at the VLT. So what is the low wind effect? You can see here observations that are not affected by low wind effects on the left. And then we have this effect happening that caused some really low spatial frequency error on your, and in the coronagraphic image, it means a lot of residuals close to your coronagraph. And you can degrade your raw contrast by a factor up to 50, as you can see on the graph here. And it's affecting the best nights where the coherence time is really high. You can see that in image here, the wind speed is dropping. This is a PSF, so a non-coronographic image of what is happening. The wind speed is going below 0, and you can start the core of the PSF to become fainter. The first error ring becomes really asymmetric with lobes appearing, and sometimes even what we call the Mickey Mouse. That's why the low wind effect was nicknamed the Mickey Mouse effect. And especially now that the wind speed really dropped to 0. So here is a summary of what is happening. I won't have time through this lecture to explain you the physical reasons of that, but it's now pretty well understood. The spiders get cold, are exposed to the night sky, get colder than the ambient air, and you have errors on the that the wavefront sensor cannot cope with. And all telescopes are not equal with respect to this phenomenon. The thicker and the wider your spiders, so the spiders are holding the secondary mirror, the worse the effects. And some telescopes, like Keck, for instance, that have very thin circular spiders are not affected, while others, like Subaru, have really thick and wide spiders that suffer a lot from these effects. So it makes a big difference. How can we mitigate that? We can do that in hardware and apply some low emissivity coating to really mitigate at the roots this problem that was done on the VLT. And you can see the effect of this low emissivity coating applied on the two graphs that I see here. So low wind effect doesn't occur for wind speeds that are larger than 3 meters per second. So you can see that the raw contrast histogram is about the same before coating and after recoating. But for small wind speeds, you can see that before recoating, there is a big difference. So there is a big difference in terms of contrast before coating and after recoating the spiders. So it improved a lot. There are also some software solutions. You can use a different model basis to control your adaptive optic system, including some piston tip tilt on a pupil on each quadrants of the pupil. That's an interesting paper by Nicolas Pourret, published last year. And you can do also some kind of focal plane wavefront sensing to directly sense the low wind effects and correct for it. And there are here various references of papers dealing with that. And the last point that I would like also to say is that low wind effect doesn't affect only the inner parts of your close to the coronagraph in your focal plane image, but you can also see here in this movie that the spiders become apparent when you have low wind effects, and they tend to blink. So sometimes they're there, then they disappear, they reappear again. And it may be, you may think that it's not really an issue, but actually when you try to subtract your star, if you haven't well evaluated this contamination by the spiders in your focal plane image, by the spiders of the telescope, you can lead to wrong detection of disks, which is what happened to me, for instance. In this image, you see here an image where you clearly have the track of the spiders and some flux seen here in between the two spiders, and this is just due to the spiders sweeping in angular differential imaging this area of the image and leaving a track, and it's not due to a disk. So we confirmed later on that this disk was actually not detected in this series of images. Let me go through another error term, which are the non-common path aberrations. So that's another problem, and we can do some kind of focal plane wavefront sensing to correct for them. Here is what happened before correcting for the non-common path aberration, and after applying a correction, you see that the wavefront is flatter, and you can really increase your contrast in the well-corrected region. your image. And in the same spirit, you can also do some dark hole digging, and this is something that Rebecca mentioned on Tuesday. So I'll be a little bit faster because I see times fly now. I'd like to say a word on the use of telemetry, which is also critical. With the new high contrast imager, we're trying to use as much as possible telemetry data to help post-processing. That can be done through PSF reconstruction or to support deconvolution. And you can see here some references of papers to do that. They did that on Vesta, for instance, that are images on the left. You see images that are being deconvolved. They are from Sphere Simple, the optical arm of Sphere. And so these are not really high contrast scenes. And in high contrast scenes, it's still a very active field of research to know exactly how to best use this information because it's not really trivial. Reference differential imaging is an area that has really developed with high contrast imagers that are much more stable. And here, you've heard on Tuesday that you can actually use a single reference or a large library of reference. That's the strength really of these large data set that are now available with high contrast imager, where you can pick and try to find the best references among this library to really get the best contrast. And you can see that for extended objects like disks, RDI, reference differential imaging, is really the only technique to be able to image those extended objects, especially the polon disks. Some new strategies have also been developed, like star hopping. So star hopping is relatively easy to understand. You would jump quickly from one star to another that are close on sky, and you keep your same adaptive optics system configured. You keep the configuration exactly the same. You just open the loop, move the telescope, close it again. And you can do that on a very high duty cycle, which means that in the end, your chronographic image would be very similar. Here you can see the two resulting images. They are really, really very similar. And that's really best to do reference differential imaging. And that helps you to improve your contrast. So in the interest of time, I will go a little bit faster just to finish with. So how far can we go? Even in reference differential imaging, where we don't suffer from self-subtraction, from angular differential imaging, we're still limited. And if we really want to go even further, we have to do some kind of simultaneous imaging, and polarimetry allows you to simultaneously record on your detector two images that have been affected the same way by the turbulence, and that helps you to reach really deep contrasts. As you can see here, this is about 45 minutes on sky, and you can see the contrast you reach is really almost, it's at the photon noise level in the well-corrected region of your adaptive optics. So it's really promising, and we can do the same in the optical. Post-processing is also key. I won't spend time on that, but really there are some dedicated processing center. For instance, we have that one in regarding Sphere, where we help people to reduce their data, and we also store all the available data from Sphere, which is relevant because you can access environmental data from the observatory, but also from global circulation models, for instance, to know the jet stream altitude, jet stream direction, if you are interested in correlations. We store the telemetry, we store all this calibration. So having all that in the same place is really an asset to allow to do some studies of the performance of your instruments. So some take-home messages. There are many contrast killers, but I would like to highlight two: the wind-driven halo or the low-order aberrations, on which I spend a little bit more time today to show you. Some dedicated observing strategy or post-processing can mitigate those, and there are also some upgrades that are ongoing to tackle the remaining limitations. What are those? You can see some the various upgrades of those IO systems as the symbols on the left. Keep in mind also that with these extreme adaptive optics system, we are really now becoming sensitive to very fine effects in the atmosphere that have been poorly studied or even known before. We mentioned the low wind effect. There is also the high altitude wind, some autoscale effects. Or in the dome, there is some enhanced or ground layer or dome seeing due to global warming that we've been monitoring on Sphere. Some vibrations, so I didn't have time to talk about vibration, but it's also an issue. Servo lag is really the main contributor to the error at small separation, and that's why all the upgrades of those instruments will include some higher loop frequency and predictive controls. And then focal plane techniques will be really key to dig further the contrast and remove the speckles. And what's coming in the horizon is really the next high contrast imager on the extremely large telescopes. And there the challenge will be really to manage to do some wavefront control over large segmented or heavily obscured aperture. But keep in mind that also the dedicated high contrast imager will only come in the second wave of instruments, and the first wave of instrument on those large telescopes will just have one high contrast mode among others. Thank you, and I'll be happy to take some questions.